We're doing electromagnetism and induction. So first question shows a motor lifting a mass, and then you have a switch with the motor here. So I get this circuit is for this motor. Shows the structure of the inside of the motor. When the mass reaches the top of its motion, the switch is open. This disconnects the battery and causes the mass to fall, or as in it reaches the top here. So and then we'll release the switch and then you will fall, and then we'll lift it. Okay, so the coil will, oh no, the coil turns as the mass falls. As the coil turns, a small voltage is produced. Explain why a voltage is produced as the coil turns. Oh, actually, it's a generator. It's not a motor anymore. Okay, explain why a voltage is produced as the coil turns. Uh, we talk about electromagnetic induction. So this is a so big. Let me just make it smaller. There there is a change in the magnetic flux. Magnetic flux linkage as the coil turns. Okay, standard Faraday electromagnetic induction kinds of introduction. There's a change in the magnetic flux linkage as the coil turns. Thus, according to Faraday, F A, I keep getting small Faraday law of electromagnetic induction. And ENF is induced. They just say why a voltage. They never ask you to justify what direction. So that's the answer. It's just like that. And it's only 2 marks. So basically, I think that's it. Let's make it longer. It's induced. Good enough. Okay, next part. As the mass falls, a student connects a wire between A and B shown in figure 10.3. Do I have figure 10.3? Oh, this one. You notice that the mass takes a longer time to fall when the wire is connected. Suggest why the mass takes a longer time to fall. Whoa. Okay, I suppose this is about Lenz Law, because Lenz Law says that it's opposite. This current will actually force it to actually reverse the thing. Yeah, counter the motion. Okay, fine. So my answer would be, let me just copy this. So that's why the mass take longer to fall. The induced current maybe I should say according to Lenz law first. According to Lenz law, the induced current is the induced current flow in a direction to produce an opposing magnetic field and produce a force in the opposite direction countering, it's not funny, in the opposite direction countering the motion, in the opposite direction of the motion. Okay, but it's 2 marks. Even according to Lenz, I must Lenz law. I must say why it takes longer, because it's rotating, so it's a moment. Okay, therefore it creates an opposing moment and cause the coil to turn slower as the mass force. Okay, so you're connecting a wire like that. Okay, next question. Simple relay used to switch a main electric motor on and off. So this is the motor. This is the main. You have this switch here. If I on it, this electromagnetic will pull the iron armature and you push it upwards. The contact will close. Okay, basically that's about it. The contact will close and then the main will be closed. The main circuit will be closed and the motor will be on. Okay, explain why the motor switches on. Or isn't that what I just said? But fine, 3 marks. Let's pull this down. Um, Current will flow through. Okay, when switch S is closed. When switch S is closed, what happened? Current flows in the coil of wire. Okay, let's call it solenoid. Current flows in the solenoid and becomes, okay, and it becomes an electromagnet, which attracts the iron armature thus closing the contacts, and closing the contact and closing the main circuit and forming a closed circuit for the main motor. Okay, thus closing the contact for the main circuit. Thus closing the contacts for the main circuit and for the motor to operate. Okay, like why the motor switches on. Finish, done. 3 marks. Okay, explain why the core is made of iron rather than steel. Well, this is the difference between the permanent and temporary magnet, right? So we just talk about it. It's 2 marks reasonably. Iron can be magnetized and demagnetized easily. Magnetize and demagnetize easily. Thus, it is suitable to be an electromagnetic. Still, is difficult to magnetize and demagnetize because you're retained in magnetism, uh, and thus more suitable for permanent magnet such as compass. I'm writing a little bit too much here, but I just want to make sure that you know your stuff. You won't minus marks, but frankly, what they want to, what I write, how can I, M-A-G, magnetize, yeah, okay, frankly, that's just it. Next, this is the same question? No, it's not the same question. Or it could be the same question. Anyway, the coil wire wrapped around a cardboard tube with no core. Should be a different question. There's an electric current in the wire in the direction shown by the arrows. That's the cardboard tube. Cardboard. So it's just made of paper. Coil of wires. Mark the end pole. So okay, very easy. Look at the direction of the wire using your right hand grip rule. Right hand grip rule. You can see that right, your hand is gripped in this way, and then your thumb will be pointing here. So this is your right hand grip rule. Right, your thumb will be here, means north is on this side. So north is here. Okay. Next, the supply of current to the coil is removed. No, this is a different question. This is a transformer. The coil is then also the supply of the current to the coil is removed. The coil is also removed and reused. Oh, it's the same question. The coil is also removed and used to make a transformer with an alternating current of 3 volt as shown. Explain how the alternating current cause the primary is to light up. Okay, simple. Basically, just get used to all this explanation. It's almost the same. Changing magnetic flux, etc. Is 2 marks. Okay. But in this case, we have an alternating current, so we have to make sure of that. The alternating current in the Pembury coil produces a changing magnetic field, or you can say causes the magnetic actually changing magnetic field easier. Magnetic flux linkage to change. Magnetic field okay. These causes changing of magnetic flux linkages within within the secondary coil. Continuously, they will say this causes continuous changing This causes continuous changing of magnetic flux linkages within the secondary coil and induces an EMF in the secondary coil. Again, reason because of Faraday law of electromagnetic induction. I don't think I want to write it here. And, and then what did they say? But I still have to talk about lamp lighting up, so I'm not going to talk about this. This is only 2 marks. Induce an EMF in the secondary coil. The induced current, since there's an induced EMF, there will be an induced current. The induced current then flows through the light bulb and lights it. Okay, this one I want to write. The transformer has 1,200 turns on the primary coil and 400 turns on the secondary coil. Assume the transformer is ideal and does not have any power loss. Okay, there's no power loss. First, let me see. 1,200 to 400. This is a 3:1. But what's the voltage? 3 volt. So 3 volt becomes 1 volt. Primary coil is 0.25. So power in primary coil is IV. So it's 0.25 times 3, which gives me 0.75 watts. So power in secondary coil is the same because there's no loss. And we know the voltage is 1 volt. Calculate, multiply by I, which is what we want to find, 0.75. So your I is just 0.75 ampere. Yep. Simple, easy, 2 marks. Okay, next question on transformer. This looks like a very standard transformer. I can't tell how many coils is it here, so I don't think that's what they want me to calculate. Suggest why the coil is laminated. Okay, very straightforward question. But very simple. But I think most students might not have seen such question before. So it's good that they asked this question. Let me just pull this out. If you study into why is it that the ideal transformer is not 100% anymore, then you will have one reason called the eddy current. So why we actually laminate the coil is to reduce the impact of the eddy current. Okay, so why is the coil laminated? This is to reduce the the size of eddy current, to minimize, to reduce the the effects of eddy currents. Is to reduce the effect of eddy current, which is formed in the transformer. Or we limit their size because we eliminated it in the transformer. Okay, can, because it's only 1 mark. Using Faraday law of electromagnetic induction, explain why a transformer will not operate using a direct current. This is like the opposite of what we had earlier on, where you have the AC and then they ask us to explain why is there a current. So it's the same thing. It's just a bit, you just need to adjust the answers a bit. Okay. Why a transformer will not operate? Okay, then since they say a direct current, so we start from a direct current. Direct current does not A direct current does not change direction. A direct current, no, it's not direction, does not produce a changing magnetic field. The magnetic field is actually very stable. Does not produce a changing magnetic field. Does not produce a changing magnetic field. Okay, in contrast, an AC will produce a changing magnetic field. Okay, so there's no change. Okay, thus there is no change in the magnetic flux linkages cutting through the secondary coil. By this one give more marks because he's only asking me why there's no it cannot work. By Faraday law of electromagnetic induction. By Faraday law of electromagnetic induction, there is no induced EMF, and thus the transformer cannot operate. The transformer cannot work. Okay, they say operate, then we use the word operate. We will not operate. Okay, that's it, 2 mark question. Okay, the power supply in an electric circuit is a battery of electromotive force 12 volt. State two ways. State two ways in which the EMF differ from that of alternating current. First way, AC has changing polarity. No, DC has changing polarity. Direct current has fixed polarity, while AC, the EMF EMF battery different than all. Okay, or AC has changing next one is usually the part where most students would struggle when they ask for two. We can say that DC produces a fixed or stable magnetic field, while AC produces a changing magnetic field. Okay, and then we have this circuit. Explain why YZ experience a force. Okay, you close S1. S2 doesn't matter because S2 is actually in the side branch, so the circuit is closed. Why YZ experience a force? Okay, the line YZ, the oh shit, I forgot to put paste. The line, the wire YZ has current flowing through it and produces a magnetic field. This magnetic field interact with the magnetic field of the magnet and thus produces a force in the direction according to Fleming's left hand rule. Okay, 2 marks. Should be around like that. Okay, next. Tick the box which describe the action, the direction of the force on YZ. Now this one you really have to do your Fleming left hand rule. So same thing, you just go in. Current should be into the page from Z to Y, and then the magnetic field N to S. So you should see that there's a force downward. So the answer is this one, downward. Downward. Okay. Next question. We have another transformer. See, transformer is a very hot topic. And also take note, you're not familiar with transformer, go and study. You have a primary coil. Again, I don't know how many coil there is, but it seems to have a lot of coil compared to the secondary coil. And then, oh, it's telling me 250. I do not know about the secondary coil though. They suggest a reason for using an iron core. Okay. Simple. If I don't use iron, is the magnetic field linkage will not be so good. I can concentrate the magnetic field. A reason, just a lot of reasons. Okay, I'm just gonna list a few. Maybe 2 or 3. Please go and memorize them. You can. Okay. First one. I can concentrate the magnetic field line. That's why I always, it's my favorite. Concentrate the magnetic field lines. I can also think of concentrate magnetic field line is the same as strengthening magnetic flux linkage. Yeah, okay. Why not focus on the word iron? Okay, iron is a good, no, it's a soft magnetic material. It's a soft magnetic material which is easily magnetized. And demagnetized. Okay. Okay. Two is enough lah, but you only need one. Okay. State which transformer is a step up and which is a step down. Huh? Is there 2 transformers? Oh, there's a A, there's a B. Okay, let's look at this. The primary coil of each transformer has 250 turns. The student apply various voltages to the primary coil and measures the voltage. So when you are A, let's look at A first. First is VS. VS is the secondary. This one is the VP. When it's 2 is 4. When it's 4 is 8. So it's increasing. Right. So so the first one is up. think I don't want to use this. I'll use for later. This one I'll just use pen to write. Okay, this one is step up is A, and then the other one is B. Oh, can see very clearly, right? B. When it's 4, this one is only 3. When it's 2, it's only 1. So it's half of it. The other one is 2. Okay. And this one, I also want to calculate. Hey, so no use for this box at all. Well, okay, I see already. Last year. Okay, I'm going to write. Voltage in the primary coil Vp is 10 volt. Calculate the number of turns in the secondary coil of transformer B. Transformer B, 10 volt. Let's go to... Where's 10 volt? Oh yeah, they never say. So it should be still up in this way, right? Now 8 to 10. 6. 8 is 10. Oh no, 10 to 8. Now the rest are not cutting very cleanly. This is not clean. This is very clean. 10 volt is 8 volt. Okay, secondary coil is 8 volt. So uh, 10 is to 8. So the primary coil has 250, right? Yes. So if this is 250, I prefer this ratio way of doing. So times 25 times 25. This will give me 200 turns. So number of toys is 200. Okay. A lamp rated 12 volt and 10 watts is connected to the secondary coil transformer A. It has an efficiency of 75%. Calculate the current. Okay, fine. So first thing we want to calculate the power in the primary coil first. Calculate the no, wrong. They said if it's used to light the lamp at normal brightness. So we are going to have the lamp in... Oh, we're assuming there's 10 watts first. 10 watts normal brightness. Okay, so we can, from here, we can calculate the current in the secondary coil. So P equal IV. But why do we need the current? No, we don't need. We don't need. I'm sorry, I already have the power already. So we just use the power 10. Okay, so 75% efficiency. What is the power in the primary coil? Okay, power in primary coil. 100 over 75, because there's a 75% efficiency. There's a loss of power of 75%. So we do this, we can work backwards. So we get 10 watts in the secondary side. And my answer is 10 over 75. This is like 4 over 3. Why is the answer so gross? Okay, I'm just going to keep it as 40 over 3 first. This is my temporary answer. So that's my power in primary coil. And then I want the current. 12 volt is in the secondary coil. 12 volt. My primary coil should be, if it's 12 volt in the secondary coil, the ratio is, when it's 2 here is 4, 8, 12. I think it's 2 is to 1 is to 2. It's a step up transformer. So I step up to 12. That means primary circuit should only be primary watts. Primary voltage should be 12 divided by 2, which is 6 volt. So what is the current in the primary coil? Current equal P over V. So it's 40 over 3 divided by 6, which is 40 over 3 times 1 over 6. Is it correct? Yes. 40 over 18. Why is my answer so gross? Oh, 40. 18 times 2 is 36. 36 still left 1 4. Eh? Wait. 40 over 18. 2. 36. I left 1 4. How? 4 over 18. Ugh. Yeah. Okay. Never mind. I use calculator. 2.2 ampere. 2 SF. So the current is 2.2 ampere. Okay. Sorry, I didn't have calculator with me at the moment. I will prepare next week. Next for the next question. Okay, suggest a reason why the efficiency of transformer A is less than 100%. Okay, why is it less than 100%? All the reason that you can think of, eddy current, heat loss, leakages or magnetic flux linkage, everything. They only want one. Okay, so the most easiest one is always of heat loss due to eddy current. Heat loss due to eddy current in the core. Another one for you, leakages of magnetic flux. This is also the reason why you need to use a iron core so you can concentrate it. But still, you might leak. In fact, you will leak. The magnetic flux linkage, magnetic flux. Okay. One more I remember. Resistance of the coil, because we are assuming that it's a wire, it has very low resistance, it has zero resistance, but that's not true. So there will still be heat loss. Heat loss still to resistance of wires of coil of the coil. We all know this is wire, copper wires of the coils. Can. So any one of you, any one of that is good. You can just use eddy current. I think that's the easiest. Okay, so that's the reason. Okay, next question. We have another. No, what is this? I thought it's another transistor. No, I thought it's another transformer. Okay, it's not. It's not. It's a solenoid. This seems to be a magnet. A wire is wound around a soft iron core. Yeah, you're forming a magnet. A solenoid is connected with a 12-volt battery and a variable resistor. There is a gap in the coil. The magnetic field in the gap is uniform and vertically upwards. Okay, complete the circuit by adding the circuit symbol for a battery. Wow, so easy. Shiok. Okay, let's just draw. Oh, okay, one long, one short. Okay, I draw in the battery. What else do they want? Wait, what did they say? There's a gap in the core. The magnetic field in the gap is uniform and vertically upwards. The magnetic field is vertically upwards. If the magnetic field is vertically upwards, is it? In the gap, this gap is vertically upwards. Okay, so now you have to understand how it works. This battery, I think you need to draw in the proper direction. What it means is in this gap here, the magnetic field is in this direction, upwards. Which means to say this part is north and this part is south. But you see, this is a bit like called a horseshoe magnet. Okay, it's not that kind of normal standard magnet that we use. The magnetic field actually go one round, so it's actually like this. So we know that it's doing this. So the magnetic field will do this. Yeah, that's why you'll come out from here, and then you'll go in here. You'll do this. It's actually doing this. So at this point here, the magnetic field is downwards. You use your right hand grip rule. You can see that all this is pointing in this direction. All the current here. So if the current is pointing in this direction, then the current must be flowing through the battery in this direction. Of course, it's the battery that is causing the direct flow in this direction. but we didn't know the battery yet. So now we know. So the battery must be, the positive terminal must be on top and the negative terminal below. If you roll reverse, I don't think they will give you the marks. Oh, yeah. This question is a lot harder than what it seems. Okay, without replacing any component, how the electric circuit could be used to increase the strength of the magnetic field? Well, you cannot change component. That means you cannot change the magnet, you cannot change the battery. The usual things that we like to change. Easy, because they already put an extra component inside, if you notice, which is the variable resistor. So should we increase? We want a higher current, right? So we should decrease the resistance. That will increase the current in the solenoid. Okay, we can decrease the variable resistance, the resistance of the variable resistor, resistance of the variable resistor. Which will increase the current flowing through the solenoid. Okay, next, horizontal current carrying wire PQ in the gap. Now we know the gap is already upward magnetic field, and we have this current. Describe the effect of the magnetic field on PQ. So there's a force. Okay, use your Fleming left hand rule. Your current is your middle finger, and then your gap upwards, right? It's upward, yes. So can you see that there is a force out of the page or out of the paper? Yeah, describe the effect. There will be a force acting on PQ, and the force is directed out of the page. Or two component, that's why 2 marks. I feel that is the case. If not, I can't think of anything else to write already. That should be the case. Aha. Okay, let's write. The current in PQ is from left to right, yes. Okay, I don't think they want you to write using Fleming left hand rule. You just use Fleming left hand rule and write the thing. So there will be a force. There will be a force acting on PQ in the, okay, don't need inner what, just out of the page. Out of the page. Oh, a lot of transformer question. Okay, so it's a simple transformer. Explain how a transformer works. Oh, I thought give me 5 marks. I don't know how to answer. Yeah, 3 marks still okay. Still 3 marks is still okay. Okay, let's try. Okay, it's like writing essay. Okay, so first thing you must say that it's a AC, as the alternating current. Flows, you create flow through the Pampri coil. It generates a changing, continuously changing magnetic field. Since it's 3 marks, I'm going to talk about iron core. The soft iron core links the changing magnetic field lines to the secondary coil. And it will experience a changing magnetic flux linkage according to Faraday law of electromagnetic in induction. There will be an induced EMF in the secondary coil. Okay, I think this is giving 3 marks.